All right, let's dive straight in. Computational geometry. Sounds a bit like something out of a sci-fi film, doesn't it? Maybe a bit complicated, a tad intimidating? Well, I'm here to tell you it's actually incredibly cool and way more straightforward than you might think. It's all about shapes, computers, and making them work together. Imagine you're trying to explain a drawing to a computer. That's where this magic comes in. It's the secret sauce behind so many things we use every single day. Pretty neat, eh? So, what is it really? Think of it like this. You know geometry from maths class, right? Angles, circles, triangles, all that jazz. Now imagine teaching all those rules to a computer. That's computational geometry in a nutshell. It's a branch of computer science that deals with algorithms for geometric problems. We're essentially giving computers the ability to see and understand shapes and spaces. This means they can solve problems that involve positions, sizes, and the relationships between different objects. It's like giving your laptop a pair of 3D glasses and a clever brain for figuring out spatial puzzles. Why do we even bother teaching computers about shapes? Well, because our world is full of them. From the buildings we live in to the routes we take to school to the amazing graphics in video games. Computers need to understand this geometry to help us navigate, create, and explore. Computational geometry provides the tools and techniques to make that happen. It's all about making computers smarter when it comes to the physical world. It's not just drawing pretty pictures. It's about solving real complex problems using the language of shapes. This field is super important. It's not just some dusty old corner of computer science. Nope. It's vibrant, it's growing, and it's powering some of the most exciting tech out there. Think about self-driving cars needing to understand the road or animation software creating lifelike characters. That's computational geometry hard at work behind the scenes. It's a fundamental building block for innovation. And the best part? The basic ideas are actually quite simple to grasp. So stick with me, and let's explore this amazing world together. Let's get down to basics, the absolute fundamentals. In computational geometry, everything starts with some very simple ideas. Think of them as the Lego bricks we use to build all sorts of complicated and awesome things. The most basic brick of all? That's the point. A point is just a specific location. It doesn't have any size, no width, no height. It's just a dot on a map, a coordinate in space. Like the exact spot where you dropped your ice cream last summer. Tragic, but a perfect example of a point. Next up, we have lines. If you take 2 points and connect them with the straightest possible path, boom, you've got a line segment. If it goes on forever in both directions, that's a line. Lines help us define edges, paths, and boundaries. Think about drawing a square. You need 4 points, and then you connect them with 4 line segments. Simple, right? But these simple lines are incredibly powerful when computers get hold of them. They can represent roads, wires, or even the gaze of a character in a game. Then we start combining these lines to make shapes. Triangles, squares, pentagons, hexagons, these are all called polygons. A polygon is just a flat shape with straight sides. Your computer screen is probably a rectangle, a type of polygon. The stop sign at the end of your road? That's an octagon, another polygon. Computational geometry gives us ways to describe these shapes precisely, so a computer knows exactly what a square or a triangle is, how many sides it has, and what its angles are. It's all about clear definitions. And it's not just about 2D shapes like drawings on paper. Oh no, we go 3D too. Think about a cube, a sphere, or a pyramid. These are 3D objects, and computational geometry has ways to represent them as well. Imagine building a complex model of a car or an airplane on a computer. That model is made up of thousands, maybe millions of tiny points, lines, and flat surfaces, often triangles, all fitting together perfectly. These are the fundamental building blocks, the digital DNA of everything geometric. Ever wondered how those amazing computer-generated scenes in movies and video games look so realistic? Or how your favorite animated characters move so smoothly? Well, you can thank computational geometry for a massive part of that. It's the unsung hero working tirelessly behind the screen. When you see a stunning landscape in a game, or a detailed 3D model of a spaceship, that's all built using geometric principles. The artists and programmers are essentially sculpting with digital clay, defined by points, lines, and polygons. Think about creating a 3D model of a dragon, for instance. The artist will start by creating a wireframe mesh. This mesh is made up of thousands or even millions of tiny interconnected polygons, usually triangles. Computational geometry algorithms help to create, manipulate, and smooth these meshes. They make sure the dragon's scales look sharp, its wings curve realistically, and it doesn't accidentally poke its own eye out when it roars. It's all about defining that complex surface in a way a computer can understand and render. Then, there's the rendering process itself. That's when the computer takes all that geometric data and turns it into the final image you see. This involves figuring out how light bounces off different surfaces, which parts of objects are visible from the camera's viewpoint, and how to create shadows and reflections. Computational geometry algorithms are crucial here. They help determine visibility, what's in front and what's hidden. They help calculate intersections of light rays with objects. It's like a super fast, super smart virtual photo shoot happening many times a second. And it's not just about static images. When characters move or objects interact in a game, their geometry is constantly being updated and checked. Does the hero's sword actually hit the villain's shield? That's a collision detection problem, a classic computational geometry task. Is the character standing firmly on the ground or are they floating slightly above it? Again, geometry to the rescue. So next time you're blown away by some incredible CGI, remember the clever shapes and algorithms working hard in the background. It's pure geometric magic. Now let's talk about robots. From those little vacuum cleaners whizzing around your house to giant robotic arms in factories and even self-driving cars, they all need to understand the world around them. And a big part of that understanding comes from, you guessed it, computational geometry. How does a robot know how to get from point A to point B without bumping into everything? How does it figure out the shortest, safest, or most efficient route? It's all down to clever geometric algorithms. One of the biggest challenges for any mobile robot is pathfinding. Imagine your robot vacuum cleaner. It needs to clean your entire living room, but it also needs to avoid chair legs, the sofa, and your sleeping cat. Computational geometry helps the robot build a map of its environment, perhaps using sensors like lasers or cameras. This map is essentially a geometric representation of the room with obstacles marked out. Then, algorithms kick in to find a clear path through this mapped space. It's like solving a maze, but with much higher stakes if you're a car. These pathfinding algorithms often involve breaking down the space into simpler geometric regions. For example, the robot might identify all the free space and represent it as a graph of connected points. Then it can use algorithms like A-star or Dijkstra's algorithm to find the shortest path between its current location and its goal. These algorithms are super smart at weighing up different possible routes, considering distance and whether a path is blocked. It's all about making intelligent decisions based on the geometry of the situation. Beyond just finding a path, robots also need to understand their own shape and how they can move. This is called motion planning. A robot arm in a factory, for example, needs to reach a specific point to pick up a part, but it has joints and links, and it can't just pass through itself or other machinery. Computational geometry helps model the robot's configuration space, all the possible positions and orientations it can safely be in. This allows it to plan complex movements without causing any expensive crunches or bangs. Smart, eh? Okay, so computational geometry isn't just about drawing things. It's actually packed with incredibly clever algorithms that solve all sorts of fascinating problems. These are like the secret codes or, special recipes that tell computers how to deal with shapes efficiently. One classic example is finding the convex hull. Imagine you have a scatter of points like thumbtacks on a corkboard. The convex hull is kind of like stretching a rubber band around all the outermost thumbtacks. It's the smallest convex polygon that encloses all the points. And this is super useful in things like image processing or pattern recognition. Another brilliant concept is the Voronoi diagram. So picture this. You have a bunch of post offices scattered across a town. A Voronoi diagram would divide the town into regions, where each region contains all the houses closest to one specific post office. Basically, if you live in a certain region, you know which post office is your nearest. This has some amazing applications. It can be used in network design, finding the nearest facility, or even in modeling crystal growth. It's all about dividing space based on proximity to a set of points. Then there's Delaunay triangulation, which often goes hand in hand with Voronoi diagrams. If you connect all the points whose Voronoi regions share an edge, you get a set of triangles. But not just any triangles. These triangles have a special property. No point is inside the circumcircle of any triangle. That sounds a bit technical, but it basically means the triangles are as well shaped as possible, avoiding those long, skinny ones. This is fantastic for creating meshes for three-dimensional models, for terrain generation in games, or for interpolating data across a surface. And of course, we've touched on shortest path algorithms and collision detection. Finding the shortest path isn't just for robots. It's actually what your GPS does. Collision detection, figuring out if two objects are touching or overlapping, is vital in games, simulations, and robotics. These algorithms need to be super fast, especially in real-time applications. They often use clever tricks like bounding boxes, simple shapes that enclose complex objects, to quickly rule out collisions before doing more detailed checks. So yeah, these algorithms are the real workhorses of computational geometry. You might be surprised how much computational geometry you carry around with you every single day, probably right in your pocket or bag. Your smartphone, for example, is a little powerhouse of geometric calculations. Think about your mapping app, like Google Maps or Apple Maps. When you ask for directions, it's not just pulling up a picture of a map. It's using sophisticated computational geometry algorithms to calculate the shortest or fastest route. Considering roads, turn restrictions, and current traffic conditions, that's pathfinding on a massive scale. Ever used a QR code? Those funny-looking square patterns? Yep, computational geometry is involved there too. When your phone scans a QR code, it needs to identify the square shape, locate the alignment patterns, those smaller squares within the code, and then decode the data. This involves image processing techniques that rely heavily on geometric analysis to find features, correct for perspective distortion if you're scanning it at an angle, and ensure it reads the information correctly. It's a tiny, everyday marvel of applied geometry. What about image recognition and augmented reality? When your phone camera can identify a famous landmark, or when an AR app overlays virtual furniture in your living room, that's computational geometry flexing its muscles. The software needs to understand the three-dimensional structure of the scene from a two-dimensional image. It identifies planes like floors and walls, tracks features, and figures out perspective. This allows virtual objects to be placed realistically within the real-world view. It's like your phone is constantly solving little geometric puzzles. Even something as simple as arranging icons on your phone screen or designing the layout of a website so it looks good on different screen sizes, responsive design, involves geometric principles. How should elements be spaced? How do they resize and reflow? While not always complex algorithms, the underlying concepts of position, dimension, and relationship between objects are pure geometry. So the next time you use your phone, remember there's a whole lot of clever shape handling going on under the hood, making your digital life smoother. So, we've seen all these cool applications from blockbuster movies to life-saving robots, but why is computational geometry such a big deal in the grand scheme of computer science? Well, one of the main reasons is efficiency. Many real-world problems, if you try to solve them naively, would take computers an absurd amount of time. Imagine checking every single pair of atoms in a complex molecule simulation for collisions. It would be incredibly slow. Computational geometry provides clever algorithms that can solve these problems much, much faster. This field teaches us how to think about spatial problems in a structured way. It gives us a toolkit of techniques for representing shapes, for querying relationships between them, and for transforming them. This kind of structured thinking is vital for any computer scientist or engineer. It's about breaking down complex problems into manageable geometric parts and then finding elegant and efficient solutions. It's a fantastic way to develop your problem-solving skills, even if you don't end up specializing in graphics or robotics. The logical thinking it fosters is universally valuable. Furthermore, computational geometry is a fundamental enabler for so many other areas of computer science and beyond. Artificial intelligence relies on it for perception and navigation. Data science uses geometric concepts for clustering and visualizing high-dimensional data. Scientific computing uses it for simulations in physics, chemistry, and biology. Even fields like geographic information systems, urban planning, and molecular biology depend heavily on geometric algorithms. It's a foundational layer that supports a huge range of advanced applications. Ultimately, understanding computational geometry gives you a kind of superpower. It allows you to bridge the gap between the abstract digital world of computers and the tangible spatial world we live in. It empowers you to create tools that can see, understand, and interact with shapes and spaces in ways that were once pure science fiction. Whether you want to design the next hit video game, build intelligent robots, or solve complex scientific mysteries, a grasp of computational geometry will be an incredibly valuable asset in your toolkit. It's about making computers truly world-aware. We've covered some awesome basics, but believe me, the world of computational geometry is even bigger and more exciting than what we've touched on. Researchers are constantly pushing the boundaries, tackling ever more complex problems. One huge area is dealing with massive data sets. Imagine trying to process geometric data for an entire city, or the incredibly detailed scan of a human brain. Developing algorithms that can handle this scale efficiently is a massive challenge, leading to new techniques in data structures and parallel computing. Another fascinating frontier is computational topology. This is like geometry, but it focuses on properties of shapes that don't change when you stretch or bend them, as long as you don't tear or glue bits. Think about how a coffee mug and a donut are topologically the same. They both have one hole. This field helps analyze complex data shapes, find hidden structures, and is even used in areas like understanding neural networks and artificial intelligence. It's a more abstract way of looking at shapes, but incredibly powerful for certain types of problems. Then there's the ongoing quest for more robust and practical algorithms. Real-world data is often messy. Measurements might be inexact or shapes might not be perfectly defined. Traditional geometric algorithms often assume perfect input, which can cause them to fail or give weird results with real data. So a lot of research goes into creating algorithms that are robust, meaning they can handle these imperfections gracefully. This is super important for making computational geometry truly useful in everyday engineering and scientific applications. And what about the future? Think about personalized medicine, where treatments could be designed based on the precise geometry of a patient's body or a specific tumor. Or imagine truly immersive virtual reality worlds that feel completely real because the geometric interactions are perfect. Or consider advanced manufacturing like three-dimensional printing of complex structures, which relies heavily on precise geometric modeling. Computational geometry will be at the heart of all these advancements. The possibilities are mind-boggling, and it's a field that's constantly evolving and finding new challenges to conquer. So there you have it. A whirlwind tour of the amazing world of computational geometry. We've gone from simple dots and lines to the complex algorithms that power your favorite games, guide robots, and even help you find your way home. Hopefully, you've seen that it's not some scary, abstract branch of maths, but a really practical and exciting field of computer science. It's all about teaching computers to be smart about shapes, which, as it turns out, is incredibly useful for just about everything. The best part is, you can start exploring this stuff right now. There are tons of fantastic resources out there. Many programming languages have libraries that let you play with basic geometric operations. You could try coding up a simple program to draw shapes, or even try to implement a basic algorithm like finding the distance between 2 points, or checking if a point is inside a rectangle. Starting small is the key. Don't be afraid to experiment and make mistakes. That's how we all learn, especially in coding. If you're feeling a bit more adventurous, why not try a small project? Maybe create a simple two-dimensional game where you need to detect collisions between objects, or try to visualize some data using geometric shapes. There are online courses, tutorials, and open-source projects you can dive into. The computational geometry community is full of passionate people who love to share their knowledge. Look for interactive websites that let you play with algorithms like Voronoi diagrams or convex hulls. Seeing them in action is a brilliant way to understand them. The journey into computational geometry is a rewarding one. It's a field that combines the elegance of mathematics with the practical power of computer science. It will sharpen your analytical skills, boost your creativity, and open doors to fascinating career paths. So don't just be a user of technology, become someone who understands the clever principles behind it. Go on, take the plunge. Start your own geometric quest. Who knows? You might be the one to invent the next groundbreaking algorithm that changes how we see and interact with the world. Good luck, and have fun shaping the future. If you learned something new like the video, share your thoughts in comment section, and don't forget to subscribe the channel for more related videos.